Let us see one more application of Gauss's theorem. The question is, find the electric field due to an infinite plane sheet of charge. In my previous video, we had seen that how to find the electric field due to an infinite wire. This time, we consider a two-dimensional plane sheet of charge. The assumptions as before. Let us consider a thin infinite sheet of charge. Consider a point P at a distance r from this sheet where the electric intensity is to be calculated. But here we have a change. We now have to choose another point P dash which is symmetrical with P, and then draw the Gaussian cylinder in this way. So let us have a look at the diagram. As we can see, the plane sheet, infinite plane sheet of charge, again we are considering positive charge, is shown in green color. The violet is the Gaussian cylinder which is drawn, which is cutting through this sheet, and at the end surfaces we can see that the field and the area vector are parallel. The point P is at a distance r, and another point P dash on the left hand side is considered, which is in symmetry with the point P, and the plane ends of the cylinder should contain both these points P and P dash. So this is how we write it. Let us choose a point P dash symmetrical with P on the other side of the sheet as shown in the diagram. We now draw a Gaussian cylinder cutting through the sheet. The plane ends of the cylinder are parallel to the sheet and passing through the points P and P dash. We now move on to the derivation. As seen in the diagram, the flux through the two plane ends is phi E, which is equal to E dA plus E dA. dA is the area vector. So let us have a look at the diagram again. So E dot dA for both the ends we add. Integration for the total flux, integration over the area A. Since E and dA are parallel on the end surfaces, we can see that E and dA are parallel. So E dA cos theta. So the vector sign has now gone. So E dA. E is the same. So E we can take outside. If we integrate dA, we get the total area A. So flux is equal to twice EA for the two plane ends. The flux through the curved surface is 0. The curved surface is 0 because E and dA are at right angles. So if we consider this surface, we have considered the end points, end plane surfaces, the end surfaces where they are parallel. But if you consider this, here dA is radially outwards and E will be in this direction. So they will be at right angles. Hence cos 90. So it becomes 0. So what is the total flux then? Total flux is the same as 2EA. So total flux is 2EA, which is equal to Q by epsilon naught. By now you are familiar with this expression. According to Gauss's theorem, total charge enclosed by a Gaussian surface is 1 by epsilon naught times the charge enclosed by the surface. But again, since it is not a point charge, we have to find out the value of Q. So let us say that the charge density is sigma. So it's a two-dimensional surface, means sigma is the charge per unit area and A is the area. So what is the charge enclosed? Q equal to sigma A, which is the net charge enclosed by the cylinder. So now we can equate twice EA equal to sigma A divided by epsilon naught, which is a permittivity of free space. And we get the final expression E is equal to sigma by twice epsilon naught.